Mm-hmm.
Yeah.
Okay. I'm pleased to announce the lecture of our speaker today, Albert Visser, who will talk about Markov coding. So the new but actually old coding scheme in arithmetic. So we are very pleased, and please begin.
Now it's, yeah. Okay, yeah, so first putting the blame somewhere, so it's all Henk Barendrecht's fault. He when he gave when I followed my first class on the incompleteness theorems, that was given by Henk, and he gave that in I think 78 or 80 of the previous century, and he used the system piano arithmetic, but with exponentiation added. So at the time, I really felt this was dishonest and preferring theft over honest toil. And so I was really annoyed by this. And later I discovered that, or I found that Gödel uh, did prefer honest toil, and that he had found a wonderful coding trick to wit the beta function using the Chinese remainder theorem. So then, so it always occupied me a little bit. So are there other ways to do this? And in fact, not so long ago, I discovered a third way, and I will talk about that. So the second way will be also mentioned during the talk. Okay, so yeah, the main interest here is really, in some sense, uh, coding in weak systems. So where do the familiar coding tricks start? And so with coding, I mean the kind of coding that we all know and love to prove the second incompleteness theorem, but also, and that's a slightly richer idea, the development of partial truth predicates. So what do we need to make this work? And so now of course, coding has a lot of aspects, but I think the first step to get things off the ground at all is that you need sequence coding, because then you can define recursion. And what I'm after is original sequence coding. So it's the kind of sequence coding that doesn't use sequence coding to define it. So for example, in Gödel's paper, he codes sequences as products of prime powers, but to do that, he needs the beta function to define prime power at all, right? And the function, the nth prime. So yeah, so from that standpoint, I would prefer to look at the beta function and not at the product of prime powers coding. And we also zoom in on sequence coding in arithmetical series, and in particular the base series PA minus. Okay, so what is PA minus? Well, you simply start with the familiar concept of a discretely ordered commutative ring, and you simply take the non-negative part. And so given that you have the non-negative part, you can construct the ring back by the usual pairs construction of the integers. And given that you have the ring, of course, you can define, since you have the ordering, the non-negative part. So in fact, they are the same. And so the non-negative part is, in some sense, the logician's way of looking at discretely ordered rings. And yeah, so how do we do original sequence coding? So my guess is that there's an infinity of different ways of doing that, but I'm only really aware of three. There's Gödel's beta function. Then we have the Smulian coding, which really uses something analogous to number systems, and then we have the Markov coding. Yeah, so there must be many more. So the Gödel's development has already been carefully analyzed by Emil Jerbeck. So he succeeded in making this coding work in an amazingly weak series. So it's a PA minus, but he could even subtract the totality of subtraction, and then still he could make it work. And so given that you have sequence coding, then this means that the theory is sequential. And so sequentiality means that you have the coding plus also the adjunction, right? So given that you have the code for a sequence, and given that you have an element, you can add the element on top of the sequence or at the end of the sequence. And yeah, for me, Emil's result was a real surprise. So I never had expected that you could do it in such a weak series. And yeah, in some sense, I'm still amazed by that. Now, the other two approaches have something in common. So the Smulian way and the Markov way. So you first start with an interpretation of the theory of strings, and then you use this theory of strings as an auxiliary to define the sequences. So that's the common factor in both. And what you do is that you do not primarily develop sequences, but something I call strings. So they are simply strings of letters, but the alphabet that you take the strings of are simply the numbers, right? So you have strings for an infinite alphabet. Yeah, so these strings could also be viewed as multisets with ordered occurrences. Yeah, okay, so why is it interesting to look at PA minus here? Well, PA minus, I think, is a very natural base theory to start the investigation of arithmetic. So argument, it's both Richard Kay and Hayek and Putlak use it in their books as the starting point. Yeah, it gives you more or less optimal generality, since results almost always carry over to stronger theory. So it's yeah. So many people are also used to the weak theory Q, but yeah. So if you look at Q, you can easily prove, and I have already proven that Q does not have good coding properties. So PA minus is really from the standpoint of coding is really the right starting point. So secondly, PA minus is a kind of a Drosophila, so it's very easy to experiment with it. So it has recursive and perspicuous non-static models, so we are below where Tenenbaum's theorem kicks in. So you can use both mathematical methods like adding negative rational and algebraic numbers, and you can use mathematical methods like using partial satisfaction predicates. And yeah, so I have a recent example. So Ali Eniat, Mateusz Wieslow, and myself were interested in completions of series. And so, of course, we know that there's a different. So, if the series has a certain complexity, you cannot complete it with a set of a certain complexity. So, that's one kind of result. But there's a second kind of result about completions, namely, can you complete a series with or make a series, a complete series with a set of formulas where the formulas are of restricted complexity. And so a very basic result is that elementary arithmetic, also known as I delta zero plus exponentiation, you cannot complete that with sentences of complexities, a set of sentences of complexity sigma n, or in fact, you cannot complete, yeah. So what happens below I delta 0 plus x? Well, we don't know, but coming from below, so I could first prove that PA minus can be completed by a single sentence plus a set of sigma 0, 1 sentences. And then we generalize this. So the three of us generalize this to the case of I open plus the full collection principle. And so but it's nice because the result was very easy for PA minus, and then it gets more and more difficult for the more complex series. But yeah, but that's precisely, of course, what you expect of a good Drosophila, that you. And
So
what
there
I
is
like
another.
about it is that it's so
Mhm.
is it a mathematical theory posing as a mathematical one, or is it our spy in the mathematical world that cheats mathematicians in thinking that is one of their theories? So I tend to think the last, but at least it sits in the intersection of Gödelian meta-mathematics and ordinary mathematics. And as I already said, so you can use methods from both traditions. Okay, now we are going to speak about Markov coding. And so the basic idea of Markov coding is that let's first do it for the standard model. So if you start with the 2 by 2 matrices over the natural numbers with determinant 1, then then you get what I call the special linear semigroup SL2N, so which is a part of the SL2Z, which is a mathematically very well studied and well known object. And yeah, and so the amazing insight is that this group can be is freely generated by two generators. So yeah, so SL2N with matrix multiplication is generated from two elements. I will say in a moment what they are. And so this object is isomorphic to the two-letter strings with concatenation, so the free semigroup. And so what are what are these objects? Well, I call them A and B to suggest letters. So the one is this matrix, so 1, 1, 0, 1, and the other one is 1, 0, 1, 1. And it's an easy exercise to prove that these two precisely generate freely the uh, the binary strings. And so the basic thing is so that if A, B, C, D is not the identity, then either the first column is strictly smaller than the second, or the second strictly smaller than the first, and similarly for the rows. And yeah, so it gives us a four-dimensional interpretation, and it can be made since we have counter pairing in PA minus. Well, not precisely. I should have said a version of counter pairing because it's not precisely the usual counter pairing in PA minus. You can make it one-dimensional at low cost, but then this cost is still a little bit. So we'll return to that later. Yeah, so the first published characterization is due to Jacob Nielsen in 1980, but Lev told me that the whole idea was around in that time, and so that it wouldn't have surprised people. For example, Poincaré would have said, of course, that's true. And ChatGPT, when asked by me, supported Lev's impression. And then later, this insight was used for mathematical purposes by Markov Jr., and that's why I called it the Markov coding. Okay, so this has all kinds of interesting mathematical connections, of which I don't know, of which I only know a very small part. But for example, we can generate the Fibonacci numbers, right? So if we take a, so to the n, then it gets something quite innocent. One, so that simply the diagonal and n right in the right above place, and b to the n, you get the n here. But if you take ba to the n, then you already are generating the Fibonacci numbers. And I think so. So Matiszewicz beautiful argument is connected with that, right? The fact that a to the n is linear and ba to the n is exponential. So that's yeah. So that it's remarkable that so that you get by this slight variation, the one thing doesn't just has linear growth, and the other thing has already exponential growth. Okay, so yeah, and so the crucial remark is really that unlike in the Smullyan coding, the tally numerals, so strings of A's, remain small. And so that means that we can very efficiently code strings of numbers as strings of letters, namely B and then A and 0 times, blah, 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 B, A, and K minus 1 times, right? And so this works in a very weak context. So I call this such a string an Ur string, so it's really an Ur element string. Yeah, well, let's talk about the naming later. So, and so the important thing is so that concatenation here is something very, of strings is something very simple, right? So it's a matrix multiplication. So concatenation of Gödelian beta sequences, for example, is not a very easy or natural thing to do. So this has really a very pleasant way of putting these things together. So so it's an Ur string. So what is the difference between an Ur string and a sequence? Well, so my theory is that for a sequence, you need numbers, and you need a length function, and you need projection functions. So, and not in some sense created in a difficult way, but it should be given with it, right? So in that sense, of course, the Gödel's beta function fills the bill. So it's defined. Well, it's not defined with a length function, but it is defined with projection functions. And the length function has to be imposed from outside. So the Ur strings do not have all these things, right? So they are really something like multisets of these numbers, but then ordered. So what you have given is that you have the numbers and the order of the occurrences, but not the places, no numbers for the places where the things are. And if you think about it, so lots of natural examples of recursion and things like Hilbert systems, you just need the Ur strings, right? You never know to know the precise place where something is. You only need to know that something precedes something else. So you don't need sequences to work with Ur strings. But of course, you can also, since we have the Cantor pairing, easily create sequences from Ur strings by the usual trick to view a function as a set of ordered pairs. Okay, and now the plan is to extend this coding idea two arbitrary discretely ordered commutative rings, right? So I treated it now for the natural numbers, but we want it for this. Okay, so now before we are going to think about that, what we need is to first we need to say a little bit about strings. So what are strings? Well, of course, if we are looking in general over PA minus, we do not really get standard models of string series. So we have to write down axiomatically a number of properties of strings. And in fact, I think it's very easy. So there's an important point about string series. I think Tarski looked only at non-empty strings, and there's a whole tradition that doesn't have the empty string, but I'm a empty string fan, and so my systems have always the empty string. So this has the obvious properties, right? So the empty string functions as a unit, or as a zero element, you could also say. It's if the product of things is the empty string, then one of well, in fact, both of them are the empty string. We have associativity, and this is the really important thing. So that's the editor's axiom. So that says that if two strings are the same, then the whole thing can be split in three. So either you have xw as u and I as wv, or x is uw or and wy is v. I have a picture of that. Let's look. That's for a moment. Oh, here I have the picture, right? So it's called the editor's principle because it's two editors that cut a text at different places. And so this one cuts it here, that one cuts it there, and then of course there's this little overlapping part. So the AB in the picture that does it, right? So this is really the editor's axiom, and I hope that with the picture it's a lot easier to understand and to remember, I guess. And it was also a good exercise for me to use my color pencils again. And
Very nice.
okay, and then we have, of course, the cancellation principle, right? We only use left cancellation, but that's just an artifact of our way of setting things up. If you set it up differently, you would need the right cancellation. And in fact, of course, we do have both, but for the development, you only use the left one. And what we also will use that A and B are atoms, and atoms are, of course, non-zero elements, such that if the product is such an element, then one of the two will be empty. Okay. Okay. Now in this theory, extended with B and an axiom that says that B is an atom, you can verify all the desired properties of the sequence coding that's given like this, given that these xi are B free, right? So you don't really need that it's strings of A's or whatever, just that they are B free, and then you can define these things that are strings are just precisely the things that are either empty or start with B. So that's, again, a very simple definition. And in this theory, we have a good notion of occurrences, and occurrences are ordered linearly. So you really, the usual way of thinking that you know and love about sequences or about strings does apply here. And it's yeah, so the editor principle is really the crucial thing, right? The rest is more or less the trivial things. So, but Tarski really found the right principle. This really is the central thing to verify properties of strings. For example, if you try to prove unique reading theorems, you will always use the editor's principle. Yeah, and so if we have two of these Ur strings and you take the composition, then the occurrences of the B free strings in this are the sum of the occurrences in this one and in this one, and their ordering inside these things is preserved, and moreover the things in alpha will be before the things in beta, right? So those are the good properties that we want. And so to verify these good properties, the editor's principle is crucial. So without it, you get nowhere. And now we can give a quantifier-free interpretation of this theory in PA minus. And so, sorry, I should have said, of course, using the Markov interpretation with the 2 by 2 matrices, and everything is easy except the editor's axiom. And yeah, and with the editor's axiom, I really was obstructed because in my heart of hearts, I really didn't believe that you could, that it seemed so implausible that you could do this with these very weak means. And so in an early stage, I tried to do this using ChatGPT, but we got nowhere. And so neither I nor it or he could make progress. And then, but what is very easy? So if everybody, if they sit down, can do this, right? So suppose that you have a discretely ordered ring, and suppose that you have this. Then you have this editor's property, so the property that's codified in the axiom, if and only if the elements of the diagonal of gamma minus 1 alpha are positive. So this is a kind of really easy undergraduate exercise to do. And yeah, it uses, of course, that in our discretely ordered ring, we have lots of usual properties like the characterization of the inverse of a matrix, etc., right? For determinant 1. So it's you can use properties that you know and love from first year algebra. So that was easy. And then I thought, well, let's ask ChatGPT this question, but then for using this characterization, so and not for an arbitrary discretely ordered ring, but simply for the real numbers. And then it had a good suggestion, and it was proved, and it turns out to be. So it turns out to be a kind of quite perspicuous calculation, and so that yeah, so that was the pleasant surprise that we could do that. And so the second step really doesn't use the discreteness anymore. So you really need so the discreteness is all in this step, and I also have a counterexample that this doesn't work if you don't have the discreteness. So yeah, so the verification of the editor axiom was a real surprise, and that worked out. So the consequence of this is that so we do have a good theory of Ur strings, and hence also a theory of sequences, and so this gives us a new proof of the sequentiality of PA minus. So it's slightly worse than Jerebeck's, but it also gives us some nice extra properties that you do not have when with the beta function. So I think there's a kind of balance, right? So the beta function gives some good things, and non-beta function also gives some small moments. Hello? Okay, yeah. Okay, good. Yeah, I'm sorry. This is was the telephone. Okay, and but yeah, so that it's interesting to look at what so what do the strings look like, and so you can do uh, some exercises here. And so, for example, look at zx, right? So that's that's the polynomials in x over z. And so simply look at the non-negative part of that. And of course, a to the p, which is where p is a polynomial, and that's a B-free element. So also every B-free string only has occurrences of A. All these things you can prove. But however, not every B-free string is of the form a to the p. So this is the example. So if we have, for example, alpha is 5x plus 7, 5x minus 7, 25, and x squared minus 2. If you look at this string and then you sit down and do the homework and do the computation, it turns out that the string looks like this, right? It's an omega string going up of a's and a downgoing string of a's. And you see that interestingly, so this is an A string, but it's not of the form it's not of the form a to the p. So yeah. So that's the thing.
So just to slow you down a little bit. So you are looking at this model of PA minus, right? So that of x, the positive part, non-negative part, is a model of PA minus, right?
Yes,
So that's
yes.
one thing. Then this coding lives, so to say, in this model as well, and you are just checking what this particular element, so to say, or word looks like in this
What
model.
it looks so that
Mhm,
there's yeah, right. So there's this notion of the profile of such a thing, right? So we have
mhm,
occurrences. These
mhm,
occurrences are ordered,
mhm.
and you can write
The
out
order
that
type of the ordering will be omega plus omega star, something like this.
yeah, omega plus omega plus omega inverse, yes.
Mhm,
And so
mhm,
all occurrences are A's. So you have this kind of string. And there's also a second interesting lesson is that the profiles that different, so you can easily write down, well, not easily, but so it took me some time to puzzle it out, but you can write down other strings that have the same profile, right? So the profile, there's not a 1-1 correspondence, but a many-one correspondence between strings and profiles. So the profile is of course a labeled order type, right? So that's it. But the labeled, so not every alpha defines a unique labeled order type. So they have some extra identity.
mhm,
Okay, so maybe this is a good point to, well, Lev also already said, slow you down. I'm going too
mhm.
fast. So maybe there's already some questions, and then
Yeah, um, there were questions, but a few slides back, and at least with me,
Yeah.
I'm not. So one thing about terminology that you are using,
Yes.
then of course in our uh, let's say Moscow seminar, the term string is strictly forbidden hist out of historical traditions because we are using the word instead of string. So
Yes. Yes.
it's a little bit computer science terminology, string. But on the other hand, so you are using these or strings,
Yeah.
and maybe computer scientists would actually know how to call this data type because basically what you are referring to as strings, they are more similar like arrays, what they call arrays, because you can call an element of an array by its position within this array, by the
Yeah, that would
number.
be a sequence, I guess,
Yeah,
right?
sequence. That will be the sequence.
Yes.
Right. And
Precisely.
this where you have so they have of course these structures like lists where you have the uh, top head and tail, so to say, structure, and they have in Pascal there is a structure of file where every element has a successor and predecessor,
Yeah.
but this is still somewhat weaker than what you actually have here because you have a full ordering there
Yes.
on occurrences. So I don't know
Precisely.
exact terminology, but maybe someone in the audience would actually
Yeah.
be
Yeah,
able
because
to help us with this.
it's welcome that you say this because recently a referee said to me, "Urstrings is not a good word because it suggests proto-strings, which is not, of course, what is intended here, but it's a string of Ur elements. So it's
Right.
yeah. So
Yeah, also a string of or elements is also not a very good term or very good. I don't think it's really, well, any string is a string of or elements in
yeah,
some
yeah,
sense.
yeah. But well, it's a role. Yeah, but it's a role thing, right? So we are
Right.
really interested in a given universe, and so we
Mhm.
make the elements of the universe letters of the strings in some sense, right? So yeah, it's something you
Mhm.
build over a universe of Ur elements, just like you build sets over a
Mhm.
universe of Ur elements. So that
Mhm.
was my intention, but yeah, but
Mhm. Maybe final remark is that of course what you are doing here in the last part, so where you consider non-standard model of PA minus and looking at how these
yeah,
or strings are interpreted there. As you remember, there was this talk by Alexei Mesnikov, who wrote a couple of papers or studying these free groups in non-standard models of arithmetic. So
right,
presumably they using, of course, non-standard models of maybe full true arithmetic or at least PA.
yeah,
So they are much more let's say, in difficult to describe structures. And nevertheless, it's a kind of a similar activity, but more algebraically, I would say here,
yeah,
because you have a very concrete
yeah, yeah. So
something.
that it's really you don't really need the usual non-standard models, right? So
Mhm,
yeah, so we're below the Tenenbaum boundary here. So I think that's really a important thing, and that's well illustrated by this example, right? So this is a
mhm.
non-standard model, where
Yeah,
but which is completely understandable in many senses.
yeah. Had
Okay.
it been a model of PA, then you wouldn't be able to do something, demonstrate anything like that. So
No,
yeah,
no, sure.
okay.
Yeah.
Mhm,
Then the strings would have a much more predictable.
mhm,
Well, at least would be all, almost well founded, so to speak.
mhm, mhm,
Okay.
mhm.
So now. So the next step was so now we have a new way of coding, and So if we think about the beta function, I think after Gödel there are two salient important results about the beta function, namely Jerabek's showing that it already works over PA minus. And there were Bezboruah and Shepherdson who created an alternative proof of the second incompleteness theorem for PA minus. And they used this by what was essential in their setup. That was that their proofs were coded using the beta function. So what is going on here? So the paper by Bezboruah and Shepherdson is called the second incompleteness theorem for Q, but that's completely in some sense a completely misleading title, because they prove a much stronger result, and so the range of application is also much larger. And so so what I call BESH, the Bezboruah-Shepherdson theory, is the theory with a very simple language. It just has two sentences, falsity and falsity implies falsity, and proofs are really proofs in a Hilbert system where we represent the sequences by the beta function. So Emil, when I talked to him about this, immediately remarked that of course you can also use a sequence system. So there's just one sentence and just two sequences, namely bot to bot and nothing to bot, and you can do the same thing. And so what Bezboruah and Shepherdson do is they create a model of PA minus in which the following proof exists. So you have an omega type falsity, 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 and you have a downgoing omega time falsity, falsity. And so why is this a proof? Because for every falsity there's an earlier antecedent and an earlier axiom, and that from which you may conclude it, right? So it's a real proof. And so you see what is interesting. So
It's a non-well-founded proof, as many people would recognize.
yeah, but the interesting thing is you could look at two ways. You could say, well, oh, this is so trivial. Uh, why bother? But on the other hand, I think the right way of saying is how nice that we can make such a trivial looking example. Of course, they use at least for me, it was not immediately trivial algebra. So now I'm getting used to it. It's getting easier, but it's so to create this model was a lot of work. But so the idea of this proof was is of course very nice, and it's so all the work is of course to get the beta function to do this. Yeah, and so their work leaves a lot of room for variation. So you can make proofs in which you have in which you can run through all the sentences of a much richer language, so downgoing and then upgoing like this, so that you can do make a lot of different proofs. And but on the other hand, for example, if you look at their proof in their model, so what I don't know is can we add one thing here on top of this proof? Can we add something? So the whole model is from Kopf bis Fuß eingestellt precisely this proof, to make precisely this proof, right? But you cannot so maybe you can, but at least I don't know whether you can further manipulate this in interesting ways. So yeah,
but this proof is coded by by a string, right? That's or by a
Yeah,
sequence?
it's coded. The proof is coded by a sequence in this case, right? We are in the beta function, in the realm of the beta function. So it's actually a sequence, and
But by Jerzabek, this beta coding is sequential, right? So you can add an element on top of a.
very good, Lev. This is precisely the right question. No, it's
Uh-huh,
because the point is so
uh-huh.
Jerabek's trick is shortening the lengths. So the Jerabek sequences.
Okay, okay.
So
Mm-hmm.
their sequence. So I talked with Emil, and within 2 days he produced a proof that the Bezboruah Shepherdson proof is not a Jerabek proof. So
Uh-huh.
it's too
Mm-hmm.
long to be. So if you look at what Jerabek's construction does, it just gives you sequences in this model. The Arabic construction just gives you sequences of standard lengths. And so,
Mm-hmm.
yeah, so it's interesting. So this is really a proof uh, looking at all sequences, but Emil didn't use all beta sequences for his proofs, but just sufficiently short ones. And
Mm-hmm.
this one is too long. Yeah, so
Mm-hmm.
that's a kind of really uh, question that clarifies, yes, precisely the problem.
Mm-hmm.
Uh, okay, and so can we do it using the Markov coding? And uh, yeah, so of course, I try really to adapt their methods, but that didn't work, and then uh, it turned out that maybe the better idea was not to adapt their method, but well, to at least try to get something like the idea of what their object look like, right? So I try to produce something like this as the proof, and uh, and so yeah. So how to do it? So I think their method did not quite work, so they expanded a model with a number of extended rationals to make it work. But so that I didn't see how to do that, and so I used a different way to do it. Um, and it works like this. So let's start with a Gödel number m of falsity and n of falsity, and I assume that both are positive, right? So they're
Not zero.
non-negative and not zero. And and we consider a tower of elementary extensions as follows. So we start with n, take an elementary end extension m, and take an elementary end extension n. Um, of course, this is all. I'm sure this is all far too heavy, but it's a kind of uh, uh, it's pleasant. And okay, sorry, I think I forgot to say something. So these are supposed to be models of true arithmetic, full true arithmetic.
Mm-hmm.
So they're honest to God non-standard models which of a very strong theory. Again, of course, it's overkill, but why we want to specify one specific model, so why we can afford us the luxury to take this, because that will give you the uh, very nice heuristics, right? And so
Mm-hmm.
let's let's look at an element, non-standard element in M, and let's look at an M non-standard element in B in N. So that sits above that sits above the model M. And then we look at two strings alpha of BA to the M, where this is this one and this is this one, BA to the N. And so this gives us this object, right, in the non-standard model. And so this is supposed to be the Ur-string that we want. But you see the disadvantage. The disadvantage is this red comma here. So here the Bezboruah Shepherdson idea breaks down. Since we since there we cannot justify the falsity just after the comma, right? And so the whole idea is to thin out the proof and to thin out the model so that the switching point is not in it anymore. So that's the plan. And so okay, so using some basic algebra, we can see that the entries of alpha are really linear combinations of two M numbers, C0 and C1. The entries of betas are linear combination of two N numbers, D0 and D1. And the entries of pi are linear combinations of products of these numbers, right? So that's easy to see. And then we simply look at N. So the N is our big model, our biggest model, and simply take the submodel generated by CI by the ring operations. And then the whole work is to show that the CI are not in this model. Okay, so this proof, it uses characterizing what these polynomials in these products look like. And it uses a reduction system. But so the proof is slightly too much to do it, but it's interesting because it uses that C1 to C0 is n infinitesimally close to an n irrational number. So a standard irrational number, and D1 to D0, to the larger ones, are m infinitesimally close to an m irrational number. And so you essentially use this to prove that you do not have certain identities, and that you need, of course, to show that that this point is not in, right? So it's yeah. So the again, so in that case, amazingly, ChatGPT helped because it provided this idea to look at these irrational numbers. So its proof was far, far from correct, but so this nice insight that this was a crucial thing was really due to it. So yeah, the experience with ChatGPT is quite interesting. So makes the most simple, stupid mistakes, but now and then there's this kind of illuminating idea. Now the nice thing is, so the Markov coding is now this really comes into play, the four-dimensional coding. So you shouldn't make it a polynomial coding. Sorry, you shouldn't make it one-dimensional using the pairing function, but the four-dimensional thing is completely quantifier-free. And so we find that this pi in K is really the desired inconsistency proof, right? So all the properties that we need for the coding are preserved. And so in the new model, the structure of this is preserved, except that some points are missing, and especially the crucial red comma is thrown out. And so also it follows that it satisfies PA minus plus all true universal sentences, right? Since I started with since I started with models of true arithmetic, so you have all the true universal sentences, and so these are of course preserved downwards to this submodel. Yeah, and so okay, so yeah, so something to say. So interestingly, Pavel Putlak adapted the proof of the second incompleteness theorem also to prove that Q doesn't prove its own consistency. And so these results, so both Bezboruah and Shepherdson and also my adapted proof show that we that PA minus or even the strengthening of PA minus doesn't prove its own consistency under certain assumption on how the coding works. And the Putlak proof also proves that PA minus or Q does not prove its own consistency using and that proof works for a wide array of usual codings. But it's interesting to see that the fact that Q does not prove its own consistency is they're really corollaries from quite different things, right? So because the Bezboruah-Shepherdson proof is hereditary, it projects downwards, right? So given so from Bezboruah-Shepherdson, that follows that it doesn't prove that the theory doesn't prove the consistency of this very weak theory, and hence it doesn't prove its own consistency. But that's preserved downwards, right? So it also follows that Q doesn't prove its own consistency. And it also proves something that does not follow from the usual method, that R doesn't prove its own consistency, right? So it projects downward, where the Gödel result is essential, it projects upwards, right? So if we have suitable extensions of the second incompleteness theorem, so these extensions also will satisfy it. So that's the important difference here. Yeah. So note, of course, the advantage of the Markov coding is that since concatenation of strings is so simple, that is that here we still have that we can manipulate those proofs, right? We can still concatenate them, where this is not possible with the original Bezboruah-Shepherdson proof, at least. So I don't have a counter argument, but at least it's not clear at all how to do that. Okay, and so this.
May I ask a question at this
Yeah.
point? So where
Yeah,
was it essential that in this proof, where was it essential that these models M and N satisfied a considerable part of arithmetic? So where was it?
Yeah, so it's okay. So of course we need to do things, right? So if
Mhm,
so, first is to we have to think of extending the thing
mhm,
with the analogs of the rational numbers and the analogs of some
mhm,
algebraic numbers, and um, yeah, so we need some usual facts about the natural numbers. So in fact, I import well-known facts about algebra, about so if we iterate determinants, then what is the diagonal form of those things, and so what are the eigenvalues of those things, right? So And these are facts that of course are all exist in the natural numbers. And so I adapt them. But I predict that if you look at it carefully, so probably it can be all brought down to maybe EA or uh, yeah. So as I
Yeah.
said, I thought it would be luxurious not to have to worry about what precisely is needed. But I think it
Mhm.
once we should be able to get it down a lot.
Mhm.
Because so for example this construction of the because we for example we do not need to take an algebraic the real algebraic closure. We only need two
Mhm.
algebraic numbers, and so these are approximated by when we define these in fact by a sequence of approximations. So it's really uh, but we need, for example, the proof that such an algebraic number is not rational, for example, right? So
Mhm.
so
Mhm.
this kind of thing. So, but I predict that if you really if you now sit down and then think about it, then it uses,
Mhm.
of course, far less than true arithmetic, and so piano will certainly be enough, but so one could hope for EA or something much weaker. But on the other hand, I'm not completely sure what it would deliver us, but it's a kind of
Yeah. Yeah.
interesting interesting thing.
Okay,
Okay.
there is a question in the chat,
Yeah.
which I
Can you read
can.
it?
So, yes. Where is the line between theories which we have for which we have the usual version of Gödel's second incompleteness theorem in the sense of projections projecting upwards, and theories for which this downward projection version of the result holds. So essentially,
Yeah.
have you any idea how to generalize this theorem from PA minus to some larger class of theories, and what would this class would be?
Yeah. Okay. So the the current so the boundaries of the current knowledge are um, for Bezboruah Shepherdson, it's really PA minus plus the true universal sentences. So
Mhm.
I think the real thing that we would like is to find some version of Bezboruah Shepherdson for I open. So I think that would be the kind of interesting next thing to think about, right? Can we get this? Can we get this for I open? That would be kind of uh, great thing. So I don't know. So that's open. It's so I was pleasantly surprised that I could get a little bit stronger theory than Bezboruah and Shepherdson themselves. But of course, it is dependent on your sequence or string coding. Um, Secondly, for the first incompleteness theorem, that of course there we know a lot more. So the weakest thing is very roughly interpretation of Q, right? So if we have a CE theory that interprets Q, we do have we do have the second incompleteness theorem using the Gödelian methods. Of course, to get it to for PA minus, it's a lot easier. So Putlack had to put in a lot more work to get Q, right? So that's Q turned out to be uh, quite complicated to really do it. So that you need really some extra ideas, but you can do it.
Mhm.
Um, and we can, of course, get as well known, people have studied Q very carefully, so we can make it we can make it weaker, right? We don't need, for example, that the addition and multiplication are total functions. We can make them partial, etc., etc. So we can go a little bit lower than Q by various tricks. So yeah. So this is what is known, and of course, if we allow ourselves to go beyond arithmetic, so there's a lot of weak series that could also be used as our starting point for the second incompleteness theorem in the Putlag style, right? We could use adjunctive set theory or some very weak series of concatenation, etc., etc. So that's it's yeah, there's a lot known, but it's very roughly Q. That if you interpret Q, then you are there.
Okay, so
Yeah.
there is another question from somebody called Harvey Friedman.
Ah, Harvey.
Oh,
Hello.
we don't know whether it's a real one, but nevertheless, judging by the question, it
I
could be.
am
So
AI.
let's, yeah. So the question
I am
sounds
the
like,
AI.
okay, okay,
Okay,
nice
now.
to see.
Oh, this image is very well done. Yeah.
Okay, maybe you will ask it yourself, Harry. Then, now that you are here, so.
All right. Well, does any of this interact with the purely monotheoretic forms of Gödel's second that are coding free? For example, it might connect up with this if there were interesting alternative notions of interpretation.
Yeah, as far as I know, but I probably don't know everything, is that all of them are used slightly more, are slightly in the part where you have still more than you have in PA minus. But yeah, it would be very interesting to see whether that was true. And so certainly for Bezboruah Shepherdson, nobody ever thought about how that about more abstract formulations of that, right? So
It's a very natural question, in fact, in this
yeah,
context,
yeah,
because really, if it is a result about a peculiar coding, it's one thing. But if it is a
yeah. No,
coordinate-free
absolutely.
result, then it's about the theory. So it's
It's yeah, so
mhm.
it's but so of course yes, because the so in the usual formulations of the sec for of G2, of course you have this quantification over reasonable Gödel numberings, and so so the model theoretic versions of course get around that. But yes, as far as I know, all these nice things use a little bit more. Theory, right? So if we think of this definition of consistency in terms of uh, uh, internal extensions of a theory, etc. So as uh, that uses more induction, as far as I know. But yeah, it's a good question, Harvey.
Well, the AI asked a good question. I got,
Yeah, yeah. Sometimes, yeah.
was this Chat GPT's question or was it the real Harvey Friedman's question?
Yeah. Well, it turns out that chat is very bad at asking critical questions. So they should really
Yeah, so it was
they
probably
really should
it was
create
probably mine.
a
Yeah.
nasty version. So that would be much better.
Yeah, I
So
think
this
it
was
proves that it was a
this is
real
probably
Harvey Friedman.
this is probably my version of this question.
Right.
Wait a moment, I'll have to give Karen this telephone. Karen, Karen. Okay. Okay. Sorry. This is was about something that cannot be
So let's go
ignored.
to the final part of your talk.
Okay, so now the thing is, so so there was this. So I have this little paper about the Bezboruah-Shepherdson theorem, though, and there was our great friend Kreisel who criticized this and saying, well, you cannot verify the loop conditions, and hence it's worth nothing because it makes no sense to ask about consistency statements in the absence of the loop conditions, etc. So I criticize what Kreisel says and say, well, so where does this demand come from? But there's also another line is to say that to note that okay, we don't have the load conditions, but we have something that is quite close, and that's so as soon as we have PA minus and we have the Markov coding, then we have necessitation. We have Loeb's rule. So to get Loeb's rule, we need Putlack's argument. And we have, and that's the important thing, we have the second Loeb condition, right? So that, so commutation with the arrow. And so now, so this of course gives us just the system K, which is not all that interesting, but so what you need to get things off the ground is an extra box, and I call that box grullet, but it's so it's the box with the gray bullet, and it's simply defined using this fixed point equation, right? So in PA minus, of course, we have the fixed point lemma, even uniform. Well, I mean, we cannot verify the uniform properties of it, but we have the uniform, can define the uniform version. And so we can define this formula that does this. And now the nice thing is that this thing satisfies Loeb's logic, the new box. And this is verifiable in PA minus. And it turns out that this is enough to have the de Jong-Sambi-Bernardi theorem. So the fixed points are unique. So for example, here in this system, we still have a unique Gödel sentence, to mention something, right? And we still have a unique Henkin sentence. The only thing that we do not have is the explicit definability of things. So the Gödel sentence in this system is not provably equivalent to the consistency statement, unlike in the stronger series. So if we add the third Loeb condition, so box implies box, then by the uniqueness of the fixed points, so the new provability and the old coincide, right? So in fact, maybe you could think about the usual systems as having both two, but it was never noted that there were two because they provably coincided. And so if you go weaker, so then I propose that this would be the reasonable provability logic to look at. And so the challenge to Kreisel would be, so why isn't this a very nice provability logic with very good conditions? And so, yeah, so it's sound for interpretations in PA minus with the following specifications. So the box is simply provability in a Hilbert system or a sequence system using the Markov-style U-string coding. And so this one is simply produced by the fixed point theorem, which we have already in R, and so certainly in PA minus. Yeah, so we have the completeness theorem for this in upwards well-founded models where the relation with this the the relation corresponding to this is called the transitive closure of the relation for this. Unfortunately, there's no published proof. So I've been working with Tadeusz Litak, so he has a proof with that uses lots of theory, but it's not written down. And there's also a proof that uses the completeness theorem for the mu calculus, but also then you have to work out the translation. It's also not written down. So I've been thinking about a simpler proof, but until now, my most recent attempt, so it did just still not quite work out. So we are really waiting for a nice and simple proof of this modal completeness theorem. But then, of course, it's quite interesting to ask ourselves, so can we do something that is the same as Solovey's theorem? Right, so I have two conjectures, namely this W, well founded as logic, is the provability logic of PA minus. And the nice thing is, of course, that to prove that it's expected that we both use the putluck methods of proving things using shortening cuts, and we would use the methods of Bezboruah and Shepherdson to produce non-standard proofs. So for example, so the reasonable first thing is to simply look at my model or their model, and no, sorry, we should look at my model, and can we substituting the Gödel sentence for falsity, can we show that that model does not contain a proof for falsity? So yeah, I would hope that it does, but it's still open. And the other thing is, of course, so do we have this, that if PA minus proves box PA minus phi implies box PA minus psi, then we have PA minus proves phi implies psi. Of course, this thing here is an admissible rule for the provability logic. If this is indeed the provability logic, for this is an admissible rule for WFL, but it's not, yeah, but here we quantify over all arithmetical sentences, so it's the admissible rule for this admissible rule does not follow from the same admissible rule for that one. Okay, and that's it.
Okay, thank you very much. This was very interesting. Now it's official time for discussion. So let me ask the first question. So of course this is quite so transitive closure of logic such as system K with transitive closure has certainly been studied for quite some time. So this is a well-known system. So my question was, is this rule, could you show the slides with the axioms once again? So this second, this Loeb's rule, is it really necessary in the full axiomatization with 1 up to 4, or can it be?
So I think there should be a Loeb's rule. So we have Loeb's logic for the box Krullet, right? For this new box.
Right.
But I don't
you wouldn't get it without something like that, yes.
But it's not enough, because I think you also need something like box Krullet, even only if box Krullet box such axioms should also be added. So this will really come out of, so when my simple proof of the
Mhm.
the Kripke completeness theorem is
Mhm.
done, it will. I think because to do the proof you need all these extra principles, and then you prove them using Loeb's rule. But I think that
Right, right.
there will be a Loeb's rule free
Mhm.
axiomatization getting out of it, but I'm not completely sure what should be in it. But
What
certainly,
kind of version of Loeb's axiom should be there? Maybe, yeah, you can formulate well-foundedness as an axiom combining box and box dot, right? So something like that.
yeah. It's
Maybe box dot of box phi implies
but
box dot phi or something like that.
it's
Mhm.
definitely not enough to have I think to have Loeb's logic for box dot.
Box dot.
I think.
It should be some combined way. But yeah, I see, I see. So that was a, yeah, it
Yeah,
is clear. Otherwise, we will not
yeah.
get well-foundedness out of, yeah,
But
without.
it's only a matter of time left. We will get the right experimentation. It's
Mhm.
clear that this is going to
Mhm.
come out of it. Yeah, and maybe it's somewhere in the literature as you suggest, and only I'm not aware of it. It's because the modal people have been studying a lot of systems.
So this remark about the de Jong-Sambin on uniqueness of modalized fixed points, so it holds for this combined logic with box and box
Yeah,
dot.
yeah. And you
And
can of course
mhm,
easily see this within so the assuming that this
mhm,
completeness theorem is indeed the modal complete the
mhm,
Kripke completeness is indeed correct. Of course, it's trivial because you
mhm,
build the fixed points from top to bottom in the models,
mhm,
right? So,
mhm, mhm,
but yeah, so the usual proof of de Jong-Sambin simply works, but.
mhm,
It's easy to see to if you make this model with the Gödel sentence alternating, the Gödel sentence for the box
mhm,
alternating downwards, then it's clear that that's not definable. So it's easy to see
mhm,
that you don't
mhm.
have
Okay.
the explicit definability.
But nevertheless, this shows that also this box dot is unique, right? So in some sense, that's
Precisely.
nice. That's a nice aspect. So if
Yeah, and
even
it's
if it
unique,
was not present before, such a thing is unique.
and
Mhm,
indeed it will and indeed if you add. Uh, the box implies boxes for the ordinary one, then that will have the same property, and hence they will be the same, right? So it
mhm,
so overlaps logic. The new one is simply uniquely identical to the old one.
mhm. Okay. Any other questions from the audience? Okay.
Yeah. So if anybody, so then I really would like to ask. So if anybody knows more sequence codings for the weak systems, right? So
Mhm,
send me an email. So it would be great to have to add to the collection. So undoubtedly there are infinitely many such things, right? So the three that we have are extremely different in kind, and so there must be. Yeah, so I guess there will be infinitely many arithmetical tricks to do this, but yeah, I'm just not aware of them. So it would be really fun to have more sequence codings.
yeah. Maybe Yuri Matyasevich knows some other examples.
Is he still here?
Yeah,
Yes,
seemingly. Yeah.
yes, I
Mhm.
am, and I will answer your question. I have something to tell you about.
Okay. Can you tell it, yeah, for all of us, or is it not?
Sorry?
So can you perhaps comment for all of us here before you answer to Albert?
No.
Mm-hmm.
I need to look at my notes and
Mm-hmm.
correct something, but I believe I know another way of coding sequences.
Oh, that would
Uh-huh.
be great.
It would be nice,
Yeah,
yes.
so that please do send it.
But I have also a general question. So we have these three codings that we see, but for PA minus, do we have any results that indicate that these two codings behave substantially differently? So,
Uh, yeah, so that's
so we have some nice properties that quantifier-free.
I think so. I don't have it not really proven, but I think so. If you the Bezboruah Shepherdson really gives you these differences, right? So
Mhm,
uh, um, at least for the beta function and the Markov coding, right? So the point, so the Markov coding has so so it's really very difficult to count places with the Markov coding, and also defining the length function is
mhm,
difficult to define. In fact, I think
mhm,
Yuri's work in part is for a very specific case defining the length function. So that's quite difficult for the Markov coding, where it's for the Gödel coding, it's easy. But then, of course, the Markov coding has it's quantifier-free, and it's concatenation is simply multiplication. So it has very good properties there. And yeah, okay, maybe the answer is, so we know in some in some we know in some sense these differences, but so a lot of these differences are not proven differences, right? So it
mhm.
would be
Right.
nice to
That was my
really have hard proofs. You cannot do that, but
right.
I
Right.
don't think that we have that, but I think ideologically it's rather clear what yes and no, right? So, and for example, Emil had to shorten to
Mhm,
to get at even adjunction, right? And of course
mhm,
you can get uh, concatenation by
mhm,
even shortening farther. So you can do all these things, but it is difficult, right? And so the um, uh, and so to concatenate um, to concatenate two beta strings, you really have to say, well, there's lots of beta strings up to n, and then you can choose a specific a good one for the concatenation, right? So you really there's it's really a kind of complicated operation where you don't it's not the kind of real something like product or concatenation of strings or whatever. It's complicated to do these things for the beta function. Where so that's good for the Markov, and of course the fact that the Markov is quantifier free really uh, is pleasant, because the that properties in a model are projected downwards to submodels, right? That's so. In
mhm.
fact, part of my proof of the Bezboruah-Shepherdson theorem was the fact that I thought, well, what can we do with the quantifier freeness?
Mhm, mhm,
So
mhm.
yeah,
Yeah, maybe that theorem in that generality for all universal sentences added to it would not hold for beta function. coding.
Right.
Something like that. So maybe that's even false. Harvey, ask your question.
Yeah, do you know of any way of talking about the foundational significance of this kind of work on G2?
On G2.
Well, on probability of consistency in systems of various notions of coding. Is there a way to talk about? One doesn't see any direct, immediate foundational point, but
yeah,
there
yeah,
could
yeah.
be. There could
You-
be
you-
one, and maybe you have one in mind because I
I'm-
know you're very foundational.
I'm so yeah. I maybe it's not precisely foundational, Harvey, but of course there's this kind of interest in intentionality and also ways to escape that, right? So the kind of thing that we are both interested in. So of course the interesting difference between G1 and G2 is the kind of intentionality. We are interested in a kind of very specific sentences, and my interest in G2 is also has to do with yes, how do we think about intentionality? And so in the weak systems, this is put to the test in a more stringent way, right? So for example, for the Bezboruah Shepherdson, we not, at least as far as we know, not any old Gödel numbering is going to or coding of strings is going to do this. And so yeah, so it's a stress test for the usual methods, right? So if we look at them through the glasses of the weak series, what happens with them? So can we? Because the point is, so if you think about things like Gödel numberings, etc., in some sense, some strong series like piano kills all the differences, and so and it, yeah. So the question, so what is the difference between these methods cannot really be posed. It's yeah, the kind of so if you think about mathematicians, so they started looking at groups and rings, etc. Well, of course, to generate new theorems, but also to really have a refined study of reasoning, right? So this last, at least this last motivation, I think, also holds here. But yeah, I don't have a full convincing answer, I guess, right? But it's yeah.
Okay, I apologize for putting you on the spot on with such a question, but you did pretty good. You did a pretty good answer.
Okay, thanks. I did my best.
Okay, but at least also this part about the last about probability logic of this PA minus, it shows that in fact these weak theories have surprising ability to still have somehow natural properties of probability
Yeah, I know
to
it's
express. So
very strange that
that's
this
one
word.
maybe moral that can be drawn
Yeah,
from here. But
it's very nice because so even if you cannot, so even the kind of general properties of syntax need not be verifiable here, because for the provability logic we use just standard sentences, right? So it's so there's, you need nothing. So the third loop condition is of course extremely interesting. What do and has it so what do we need precisely for the third loop condition? But here we evade this simply by the fixed point theorem, which we have in because we only need the standard fixed points here, and to verify this we only need R. So yeah, it's really surprising what you can do
Yeah.
here. And so the really the crucial thing is, of course, that we have this composition of proofs. So that's the real thing you need.
Right. Okay, so we are slightly overdue, as you see. So there were discussion fully compensated the brevity of your talk.
I like more discussion, so
Yeah, that's
it's
what we
not
are.
bad.
Mhm. Okay, so thank you very much for the interesting talk. Thank you everyone and all participants for the discussion. And
Yeah.
till next time.
Okay, thank you.
Yeah.
Yeah, bye.
Bye-bye.
Bye bye. Thank you.
Mhm.
Bye.
Mhm.